All right, so we are going to learn about the number e, which means natural logarithm. So where did e come from? E has been studied for a long time throughout math history, but it was this guy right here, Euler, who really pushed it. That's why it's often said to be Euler's number. So E is approximately, we can't really make an approximation symbol, 2.71828. And actually, they've figured it to be out to be 1 trillion digits. But we're usually going to just use 2.71 or 2.72 if you round. It's used in interest and finance mainly. It's used in a lot of places. The other irrational number you know, or letter, I should say, is pi, which is the circumference of a circle divided by its diameter, and you've learned it to be approximately 3.14. Well, we're not really going to get into the history of E. We just want you to realize that it is used in carbon-based things such as AP chemistry, and it's used everywhere in finance. So if you're somebody who's interested in finance, you're going to be using E a lot. So if we're going to look at it, first of all, we're going to look at it as an exponential, not e for exponential, just so happens, but y equals e to the x. So really you're looking y equals 2.718 to the x. So it goes through the point 0, 1 because anything raised to the 0 power is 1. And it also, if I put a 1 in, see, it's about 2.718, and it still has a vertical asymptote at y equals 0. It means it gets very, very close, but it never goes below it. So now we have to clarify. We have logarithm, we have logarithm, which means base 10, and now we have natural logarithm, which means base e. So logarithm is written as log when we need base 10. Natural logarithm, now here's another thing. Natural logarithm, people say, why isn't it NL? Why is it LN? Because for the most we can say is people who worked with natural logarithms were French or European, and the adjective comes after the noun. So that's the most that people can come up with why it's ln and not nl. So for example, natural logarithm of e. This is really what it's asking. The base is e, even though it's not written there. That's what you're going to see when you see an ln, the base is e. What is the answer to this question? Remember, logarithm is fancy for what is the exponent. And now if it's ln, we just add the base e. What is the exponent of e that gets me e? Oh, well, the answer has to be 1, right? If we roll the log here, it still has to be true. E to the first gets me e. Likewise over here. What is the answer to L natural logarithm of 1? Well, the answer is 0. That's right, remember. What is the exponent of base e that gets me 1? So if you're going to write the e in there, if you're going to do rolling the log, e to the 0 is how I'll get 1. Now these are two very important common things you should remember. Much like you remember 2 times 2 is 4, you should know the natural logarithm of e is 1, and the natural logarithm of 1 is 0. Now, if you really understand logs, the next thing isn't that hard. So what is the natural logarithm of e to the 5th? Well, the answer is 5. And you can look at that a couple of different ways. We could say, well, natural logarithm of base e to the 5th gets me what? So if you roll the log, you could say e to the something gets me e to the 5th. Oh, x has to be 5. You could also look at it this way. You could say, oh, I remember my rules. 5 has to fall down in front if I were to solve this. And then I'm left with the natural logarithm of e. Oh, well, up here I learned that the natural logarithm of e is 1. So 5 times 1 should get me my x I'm looking for. So x is 5. So however you want to learn it, go for it. All right, so now we're going to do number 4, which is we're really just rewriting things again, same way we wrote base 10 logarithms. It's now that we just have base e logarithms. So if I look at this, I'd say natural logarithm x cubed, x, all right, cubed minus, because it's division, natural logarithm of e squared. So the first thing I did was handle the division by saying I'm working with the exponent, so I'm changing it into subtraction. Oh, I can't really have exponents, so this 3 falls down in front, and this 2 falls down in front. Now I can clean this up one more step, because once again, I know what the natural logarithm of e is. We figured that out back in example 1. So continually to clean that up, the natural logarithm of e is 1. Multiplied by 2 is 2. So 3 natural logarithm of x minus 2. All right, so we're going to go on to some problems now where e is actually in the problem. Because remember, I told you e was a very powerful number. It's used in finance. It's also used in population. It's used in continuous exponential growth. Again, you'll learn more about that in calculus. So a population of llamas on a tropical island is modeled by the equation. There's math. I'm just going to pull that math out. P equals 500 e to the point 0.035 t. Okay, so the first thing I want to realize right here is I've got e. Something's going to happen with that e. T represents the number of years since the llamas were first introduced to the island. How many llamas were initially introduced to the island? Well, that's easy. We know that that's 500. So our first answer is there were originally 500 llamas on this island. How many years will it take for the population to reach 600? All right, so we understand this. This is nothing new from the last time we were doing exponential growth with base 10. We want the population to get up to 600. We originally had 500 llamas. There's that E for continuous population growth, or continuous growth of something, raised to the t power. So now we know that we have got our unknown is an exponent. Now I'm going to clean this up. So the first thing I'm going to do is divide by 500, because I want to get that t as alone as possible. All right, now, anytime we were finding an unknown exponent, we had to introduce logarithms. Now, here's the funny part. You could work in base 10. You could take the log of this have your exponent fall down and take the log of e. But we wouldn't want to do that because of the special properties that we just learned about natural logarithm. So basically what you want to learn is if I want to undo base e, then I'm going to work with natural logarithm because we just learned that the natural logarithm of e is 1. Then we still have the 0.035t falling down in front. And then if I took the natural logarithm of one side, I've got to take the natural logarithm of the other side. What makes this wonderful is what I just said. The natural logarithm of e is 1. So what I have here is the natural logarithm of the left side equals 0.035t. I'm looking for t, so the last thing I'm going to do is divide by 0.035, and there it is. To find t, I have a very easy mathematical computation on my calculator. Take it out. The natural logarithm of 6 divided by 5, which is then divided by 0.035, means in about 5 years. So let's see, did they tell us to round anywhere? So it's about 5 years for that population to grow from 500 to 600. All right, so here's another problem. And once again, I just go right for the math. There's my equation. I'm going to bring my equation down here. Once I get it down here, let's see what we're talking about. A hot liquid is cooling. All right, so we're starting with something hot and it's getting cooler in a room whose temperature is constant, so that means the temperature is not fluctuating in the room. All right, we got the modeling formula. T is the temperature in Fahrenheit. That's always good to know. And is a function of the number of minutes it has been cooling. All right, so this is minutes over here, and this is the temperature after so many minutes have passed. What is the initial temperature of the liquid? This one's a little tricky. We're going to look here. We see that the initial temperature is 101. But remember, if we put 0 in here, 0 times anything is 0. E to the 0 power is 1. So at 0, when we first start this, when no time has passed, it's 101 times 1 plus 67. So the initial temperature is really 168 degrees. Tricky there. It's not just the number that's in front of the base. We have to add on how fast, remember, how far we've shifted it. All right, so what does T of 60 equals 83.7 mean? Well, we should know that by now. That means that after 60 minutes, the liquid is 83.7 degrees, and you can put the Fahrenheit on there. All right, how many minutes will it take the liquid to reach a temperature of 110? Well, just by looking at it up here, we know it's got to be less than 60, because after 60 minutes, it's down to 83.7. So that just gives us a little frame of reference that when we do this, if our answer is approximately right or not. All right, so in for T of M, we're looking for the temperature of 110 degrees. 101 e to the negative 0.037 m plus 67. Okay, so we're just going to start cleaning this up and trying to isolate that m. So the first thing I'm going to do is move that 67 to the other side by subtracting. And that comes out to be 43. We still have all of this left. All right, I'm going to divide by 101, but I'm not going to divide by 101. In other words, I'm going to keep it that fraction. Why divide out and get an ugly decimal? And here we are. How do we solve unknown exponentials? We convert to logarithms, and in this case, we choose natural logarithms. And that is because if we throw a natural logarithm on both sides so that we deal with the exponents, all right, we see that the natural logarithm of 43 divided by 101. Don't divide out 43 by 101. Just let the calculator do it when it takes the natural logarithm of it. On this side, two special things happen. We know that when we turn things into exponents, if an exponent is present, it falls down in front. But what's even more spectacular is we learn that the natural logarithm of e is 1. So in essence, a natural logarithm and the e cancel each other out because the answer is 1. And once again, I'm not going to divide this out and get a decimal approximation. I'm going to let the calculator do all the division. So here I'm going to divide both sides by negative 0.037. So I'm going to take the natural logarithm of, already forgot the numbers, 43 divided by 101, end your parentheses, and divide that answer by negative 0.037. So our answer is about 23. So if you come back here to the top, after how many minutes will it take the liquid to reach a temperature of 110? About 23 minutes.